Yep.
All right. So the paper I'm going through is a paper that I think it came out maybe last month or maybe 2 months ago. So it's very recent. And the title is Learning Function from Structure in Neuromorphic Networks. And the first author on this is this lady, Laura Suarez. And Laura Suarez has been blowing up on the fucking citations. I'm pretty sure she still hasn't even graduated, but in 2 years she's gotten almost 250 citations, which is just absurd, and it's not even on this paper. So yeah, I mean, I was a little jealous when I just looked at this, but yeah, she's doing good things. So we should all try to learn from her what she's doing. That's just killing it. So this is the sort of outline. So I'm going to go through kind of the background of the reservoir networks and liquid state machines, and then we're just going to go through some code that does very basic stuff, but it will give you enough background, I think, to understand what happens next, which is how she applies this on sort of to understand processes in the human brain, and she makes inferences out of it. And then we go through basically her main results. And then there's a couple stuff that I don't like in this paper. So I have 3 slides, stuff that I don't like. And this is, of course, I mean, a lot of this is my opinion. So if you guys want to like jump in and debate about it, I'm like more than happy to do so. But yeah, so let's get started. So the first thing is, what is this reservoir network? What is it used for? Well, basically a reservoir network is a bunch of recurrent neural networks that are just kind of hooked up in this reservoir randomly. And the idea was sort of first proposed by Wolfgang Moss in, I think, like 2002 or 2003, where basically he wanted to have some way of having a memory system. So you have this input, and this input is usually a time domain signal. So you have an input that's a time domain signal, and then you feed it into this reservoir. And the idea is that the reservoir has all these cyclical connections where the information swirls around. And once the information is in this reservoir, you have a layer that basically takes out the readings of the activity of the reservoir and then tries to reconstruct back the input. So the idea is that you have some part in your brain that you constantly put sort of new trains of information. It swirls around and you pull things out.
So is it the rebranding of Boltzmann machine?
I've heard those things together a lot.
What you're describing, what you're describing is like a premise of Boltzmann machine, as far as I understand. It's like, okay.
Right, but a Boltzmann.
Yeah, and there's 2 flavors of these that are kind of used. So there's the echo state network, and the echo state network is basically all of these elements in the reservoir are literally just a regular neural network layer. You have a tanh activation function and some weights or whatever crap, and they're literally there are weights in each of these arrows. And the other one, the liquid state machines, implements this reservoir using spiking neural networks. So you have something like an integrate and fire neurons, and they make it work with integrate and fire neurons. But for this paper, she basically uses an echo state network. So this is what we're going to go through. So here's the code break, which isn't really a slide because I'm actually just going to start going into the code. Okay, so as you remember from the figure, the purpose of it is to, have this input time series go into this reservoir, and then you're just going to reconstruct back out of it. And we're just going to go through the quick steps of how they do this, and maybe hopefully like you sort of understand what happens, and then how she changes it for her paper. So basically, in this reservoir, you have a random, she just has 1,000 nodes in the reservoir, and each of these 1,000 nodes are randomly connected to each other, described by this weight matrix W. As you can see, it's just a matrix of 1,000 to 1,000 connections.
Is this
So
somehow
each
similar
one of these
to,
dots is an edge between two areas. What's up?
is this somehow similar to the Hopfield network?
To a Hopfield network. I've also heard those things maybe referred in the same thing. I don't know exactly what Hopfield is, but I think Hopfields and echo states are, I've seen texts refer them in like similar sentences. But anyway, so the only thing that is really important here is they divide by this, what they call the spectral radius, which is just literally the largest eigenvalue. I don't know why they don't just call it the largest eigenvalue, which is what I call it in my papers, but okay, you divide by the largest eigenvalue and you normalize this matrix. And once you have this normalized, then, so you have, so YT here is the data. And the way that you basically do this whole thing is you have this this NP dot of the weight matrix W, and X is the actual time series of each of the nodes. So there's 1,000 of them. So each of the reservoirs here. This is implemented, I think, even without a neural network. So this is just literally, they just have a time series X for each one of these. It's multiplied by this W. And then there's the input comes in through U right here. So this is, this signal right here. And this U is basically multiplied by some input weighting matrix. This, I think, is all just ones literally. So it just comes in. And then there's a 10H over the whole sort of thing right here, so that, it kind of bounds it. And then this A and this minus A right here, and A is greater than 1 here, basically, I think. This is an exponential decay term. And then this is, the other term that's just sort of, the network term. And, so, you put in this thing and it's like computing this crazy stuff. And then to get back the signal, you literally just solve for this W out. So this out matrix where you literally do a linear regression on X and the original signal that you were trying to recover back out. So you solve this system, you get back your W out, and then you've trained it. So basically, you put in the signal, you see the activity, and then you basically use that activity to solve this output weight matrix. And then once you have it, then you just run it. Once you have it, you just run it. You put in whatever signal you want. You get your your activity in the reservoir. You multiply it by the weight matrix, the out weight matrix, and then you reconstruct the signal. So here's the target signals in green, and this is the recovered signal in blue. And you can see that as it goes longer and longer, the green and the blue start diverging. So the memory gets worse over time, basically. And the reservoir has some crazy activity, and the out matrix also has some structure in it, but she doesn't focus on this or on this. She really just focuses on how much can we generate back. And her main question in all of this, before I move on, does anybody have any questions on this?
Yeah, I was going to ask, does the above plot, the reservoir activity, is that in some way the frequency sort of, it looks, so the output weights, it kind of looks like the frequency domain or something. I don't know.
Yeah, I mean,
Probably some.
right now we're putting this nice science sort of looking input. I mean,
Right.
There's obviously stuff on there, and I'm guessing that some of the weight.
It looks like it extracts sort of different frequencies, and then the output weights has like the weights basically for all those frequencies to put back together the original signal. That, I don't know if it's like a dumb, but that's what it looks like to me.
It could be. I mean, it depends a lot on what is the weight. I mean, here they randomized it, but obviously there's some structure in it. So I'm imagining that some nodes are more connected than others. So they might have more higher frequencies, where some nodes might be just doing kind of a low pass filter. I don't know. But whatever the activity is, it kind of swirls around. Yeah, I don't know if you can call it. It's a messy transform. It's really a messy transform here. But anyway, so what her experiment was, okay, let's take the structure of a brain. And the way that you get the structure of the brain is, if you've seen my like my thesis or any of my stuff, you basically do a DTI, diffusion weighted tractography, and then you basically you identify regions of the brain, and then you calculate how many fibers are going between that. So she basically says that, okay, let me just use the DTI that we're measuring instead of some random matrix, and then let me define this task where I'm going to input it into certain network regions we know in the brain, and then I'm going to read out in certain other network regions of the brain, and then I'm going to see what happens. And here, what she does here is that in the experiment that the example that I just showed you in the IPython notebook, you kind of have a W in that is kind of projecting everywhere, and you have a W out that's also collecting data from everywhere. But you can of course limit it to a small region or a small area, and that makes the task of reproducing the signal a lot harder, of course. And so she's basically trying to see that if she can put the information on one side, and can you decode using from the other side, and does the structure of the brain help that whole thing? That's basically the question that she wants to explore. And so of course it's kind of confusing, what is the input and what is the output of the brain, because obviously it's not clearly defined. And so what she does is she decides that she's going to use these 7 very kind of famous areas in the brain, and she's going to cycle through which one's the input and which one's the output. Okay. And sort of
Can you zoom in? Can you zoom in, please, since you're on the slides for now?
Oh yeah, I'm sorry. I don't know.
What do you mean by cycle in and cycle out? Cycle through.
So she first, does visual to frontal parietal, and then she'll maybe do visual to somatic motor, like that.
So does she assume that everything is fully connected, or does she do it based on the DTI?
It's all based on the DTI, right? So nothing's fully connected. She starts with 66 regions, and then she further divides each of the regions somehow into 1,000 nodes. That's how she does it. But that's why you see so many dots here. So there's, I think, like a bunch of different nodes that she's inputting it in.
What type of data does she use apart from the DTI?
So she just makes a random input signal, U of t, that's I think between like 1 and -1 and whatever. And you can kind of, I think this is literally the signal she puts in right here. And the idea is that you recover the blue signal. And she does this for different. Well, I'll get to it. Basically, the way that she evaluates it is, first she creates 2 null models. So she creates 2 null models by taking the empirical structural connectivity. So this is brain regions by brain regions, and she just randomizes and rewires it and creates a bunch of them. Okay, and she has, I think, 66 DTIs. So she I think runs it on each single one of them. So she gets a distribution of results here, and then she has a distribution of randomized rewired networks here. And then the other thing she also does is she permutes the labeling of the network. So she randomizes the labeling, and she basically scrambles this around. And her hypothesis is obviously that the structure of the brain helps preserve memory in the whole circuit, right? And then the way that she quantifies her results, again, so the task is very simple. Task is just reproduce the input, right? So the way that she wants to quantify this, and I didn't quite like this. She basically takes the so this is the absolute value of the correlation. So this row is really Pearson correlation of y predicted and y true. And she literally just sums this over different time lags. So, she looks at, can you recover the signal after 1 time step? Can you recover it after 2 time steps? And so on and so forth. And she has different output weights for each tau. So, after 3 taus to recover, something that was 3 seconds ago, you need a different weighting or whatever. But basically, this is how she does this. And she calls this term memory capacity. And I don't like that she called this memory capacity, because capacity to me has a very information theory sort of meaning, like Shannon's capacity. And you have an encoder and you got a decoder. I don't know why she doesn't just do regular capacity stuff here, and she just takes this weird absolute value of correlation. And even if you just take the absolute error of correlation, just call it correlation. I mean, we're all doing functional connectivity and all this crap. Like, I'm sick of it. Just call it correlation. We all know it sucks, but like, don't just like invent a crazy new term. But okay. Anyways, she basically uses correlation. So all the plots, it's absolute value of correlation. So all the plots are going to be between 0 and 1, where 1's obviously best, 0 is a no fit. And so her main result, so here you get the main result here. Oh, and by the way, I should probably explain one more thing. So the one other thing you can do in this whole network is you can, when you randomize this W and you divide by the max eigenvalue, you basically you can then multiply it by a constant. So in this example, it was like 1.25 or something. But basically, this is a sort of a global connectivity strength of how strong this network term is versus the decay term or whatever the other terms are. And so the stronger the network term is, what you'll get is all the nodes will kind of converge to one singular sequence. And the weaker it is they'll kind of just go on their own. And so she basically defines these 3 regimes where this alpha right here is changed from 0.3 to 3.5, where below 1 it's sort of subcritical, where the dynamics basically decay to 0 if you don't put any input in. And in critical, it's right at criticality, where alpha is equal to 1, where the largest eigenvalue is 1. And then there's a chaotic regime where alpha is greater than 1. And and so she looks at, in all 3 of them, she looks at the empirical brain network, the rewired brain network, and the permuted. So these 2 are the null models, and the pink is what is supposed to do better. And the pink really only does better during the critical. So that's what I thought was really interesting. Also, these equations right here are very close to my brain network model equations, which is literally x dot equal to ax. So she's written it as a discrete step equation, but we do this continuous stuff, and she has a tan h in here, but that's also thrown into the equations here a lot too. So it's literally the same sort of brain network models, like the fine rate models that I use, but it has this nice input term coming in, and you're also trying to get back that input term. But yeah, so her value of alpha, where it does kind of the best, is also kind of my value of alpha, where I think it does best in the metrics that I use, which is mostly to see how well this dynamical system reproduces resting state sort of trajectories, like seen in like fMRI data or something. But that I thought really was cool. So like criticality or around there, or just slightly less than criticality, she shows that it has the best sort of difference between empirical and these sort of randomized networks. So I like that a lot. Also, so then what she did is, she wanted to kind of look at the memory capacity. Okay, I should probably said, so this is only for a visual encoder and a frontal decoder. So she puts the input into the visual cortex, and she decodes out of the frontal. And here she kind of I don't exactly remember where she puts the input, but she decodes out of each one of these areas. So visual, somatosensory, I don't even know what D. I think this is dorsal attention, ventral attention, limbic, frontoparietal.
Where does she get
DMN,
where does she get the sort of input signal from in terms of the visual? It's random.
It's just this random U of T. Just puts a random signal in.
Okay.
Yeah. So she's not using any real data or anything. But yeah, I mean, these plots look like
Apart from
there's
the
trends
DPI.
going on here, but I never understood these trends. The only thing that I really see is that the difference between, you know, the real one and these grayer ones are the null models. The greatest difference really just happens for all of them during criticality. And they all do kind of equally well during criticality too, which I thought was interesting. So basically, I'm thinking that, yeah, I mean, if you bias this correctly during criticality, then, you know, you have the most amount of information you put in and it kind of stays within the system without it like falling apart, basically. And then here she does another term that is slightly interesting, where she defines the capability of each of these nodes, how well it's as good as an encoder versus a decoder. And the way that she defines it is she defines the encoding capacity of the intrinsic network as the memory capacity, right? So correlation shit, as you can see, it's always been 0 and 1. Where basically when she calls it an encoding capacity, she puts the signal in to that node, and then she tries to read out exactly from the same node she put it in. So that's how she defines encoding, and she defines decoding as she puts the input into it, and then she reads out from a connected neighbor. Now, is this really encoding and decoding? No. I mean, she's using a lot of confusing terminology from like computer science in ways that I'm not super happy about. But is this a valid test? Yes. And what, I don't know. I mean, there's, you know, it looks like there's a lot of difference when it's not in criticality, but in criticality, I feel like most of the differences are gone. And she also gets this weird plot where she, you know, you see the visual system as a better decoder. And that's literally because I think the way she defined it, like the visual system is probably really good at, you know, reinforcing the image. If I had a bunch of thalamocortical loops, it would, if I put in a visual image in the visual system there, I'd imagine it just swirls and stays there. So yeah, I do see it. You can decode out of it really well. But yeah, I don't know. I mean, some of the other ones, it's kind of hard to tell really how to really think about this. But I mean, the way that I look at it is that, yeah, I mean, I think they're all equally well. I think at criticality, the dynamics of it allows you to put it in and take it out roughly the same amount. And then there are kind of results that I thought were kind of more trivial. Here, she basically, when she rewired the network, she noticed that, you know, you can see that the pink is the original network, and when you rewire it, you get a lot of connections that are further away. And this is sort of a well-known phenomenon that the network that we have in the brain is wired up so that, you know, neighboring areas are wired up mostly together. So, you know, the total wiring cost is much lower. So obviously the total wiring cost is going to increase here. And then she basically showed that, yeah, if you look at random networks divided by wiring costs, you know, the memory capacity divided by wiring costs, then you get a massive difference. And this is different than in this, where, you know, they're almost identical here. But, you know, if you divide by the wiring cost, which was obviously going to be way worse for the random network, then you can see a much bigger difference. I mean, this is kind of obvious because this is obviously going to shift. So this is definitely going to get worse. I think this is kind of I wouldn't have put this into a figure. I would have put it maybe supplemental, but okay. The other measure that she does, And I don't think she wanted to do this because I saw her preprint, which didn't have this graph. So I think this is what a reviewer really wanted to do. And I don't really think that, I mean, I really like graph theory measures when I read Barabasi doing them. But when people in like neuroscience, they just throw like path length or like modularity or whatever, I don't know what I'm supposed to get out of this. I really don't. But basically what she's doing is she's looking at all the different nodes, and this is again stable, critical, and supercritical. And what she's doing here is she's looking at how well each of those little nodes are doing in terms of memory capacity, and then she calculates the average path length from here to like the other area or something, and so I mean, in criticality, which is like the middle panel right here, these correlations are really low. Like, these don't look like anything. So I don't really think there is anything in this. I think she did this to please the reviewers, but I don't think this analysis really got anything out of it. But anyway, and then the last thing I really don't like about this is the way that she used memory capacity. I think you could use maybe a different scoring mechanism that might gain a little bit more information out. Like, for example, when I was just thinking about this, like I realized that the memory capacity, I mean the correlation between these signals are just going to get worse over time. So why not just plot that? Why not just plot it gets harder to decode at further time steps away? And I'd imagine that maybe in criticality or subcriticality, those like they would fall off faster. I don't know. I mean, I'd have to test this out myself. But in conclusion, the things that I really like about this is that, well, she's using, she's, instead of trying to look at the structure to function relationship the way that I do, which is just, simulating a dynamical system and then trying to match it with resting state, she actually puts a task in here where she's like, let me just like actually not just make the like, I'm going to make the connectivity try to do something like a memory task. And I'm just going to use this metric of putting something in one part of the brain, recovering it back out. And I think that honestly, this is a great idea, especially because I've been trying to think about how to move towards tasks in a long time. And also her equations right here are nearly identical to what I already have, except for putting an input signal in. So, I'm thinking, why not have my complicated brain network models where, sometimes these equations are even bigger, but, use an input signal into a certain part of the brain, take it back out and see how well, maybe this helps differentiate between a lot of these models that are, used to represent resting state. Maybe it'll help differentiate them more if we look at also these additional metrics, like actually use the brain rather than just, simulate something theoretical, like whatever functional, fMRI is. But yeah, so that's basically what I got out of it. Yeah, what do you guys think?
Sorry, I don't know if anyone else wants to, but my first thought is also these activations that you get back. So she shows that you have like a better decoder in the visual system, right? For example.
Yeah.
My thought with that is, so could you use this to look at, for example, disease, right? Like mental disorders. If you simulate using the DTI of someone with schizophrenia versus healthy controls, do you also see something where, for example, maybe the visual system becomes a better decoder or maybe becomes a worse decoder as you add sort of that dependent variable? Like if you simulate these things, because she does use real data for the DTI, right? To initialize the weights, basically.
Yes.
If I understand correctly. So my thought kind of goes to, can we do the same thing, but then kind of condition it on some other variable, like
yeah. So I actually had this kind of similar line of thought, not in schizophrenia, but in depression, and in a very specific case too, because right now in a lot of the DBS studies in depression, they they basically insert 2 electrodes in one on one side of the hemisphere and one on the other side of the hemisphere. And the way that they simulated it is they basically put a very strong, fast current around 185 hertz, so much faster than anything. And they're always in opposite phases. And the idea is to kind of de-link the 2 hemispheres, is that, you know, the 2 hemispheres are so strongly connected that basically your emotional landscape has shrunk so that no matter what your input stimulus is, you kind of just get stuck into the same limbic output, right? And so, you know, can we put the input signal maybe into one hemisphere and then read it out to the other hemisphere in a depressed person, where I imagine that, you know, yeah, the signal should be, you know, almost identical on the other side and is there forever, right? Versus in healthier people, you know, it degrades a lot faster. So also, I mean, having higher memory might not always be the best ideal thing what it's doing too. I think you have to be careful, but I think, yes, I think we can use this for diseases. There's definitely cases, if we go case by case on, you know, exactly how the disease is affecting the brain and what we think. I think, you know, you can define good inputs and definitely good outputs. And I think also, rather than randomly permuting everything here, which makes it kind of confusing and, you know, difficult to use this as a metric, if you use it for special cases for specific diseases where, you know, it makes a lot of sense where you would put the input current and where you would have the readout node, like maybe, you know, it would be much easier to test those models for those specific cases. So yes, I do believe that this is a great idea. Even like in like Parkinson's, maybe, you know, you want to send a signal down in the subcortical cortex,
right?
You have a very specific task in mind, rather than just looking at Parkinson's in resting state, which is very uninformative, really. You know, make them do a motor task. Then I have a very clear where I'm putting the signal in, where I want to decode, and then you see the flow through the network while you're, you know, simulating brain dynamics at the same time.
What I would
using, yeah, go ahead.
I also like it for spectrum disorders. For example, you know, externalizing symptoms with schizophrenia, or for example, autism spectrum disorder. You would expect there to be different different types of reactions inside of the network for people with mainly externalizing symptoms in schizophrenia, for example, versus internalizing symptoms. And another question I had is, do you think we can do this with real data? So for example, if we take EEG or resting state fMRI, what if we, like, how well would that transfer to this? Because she used random signals to input right now.
That's a great question. I mean, I have no idea. I was thinking maybe, you know, we do an fMRI working memory task, and I don't know, you know, we can record what the input into the visual cortex is, what it looks like in the fMRI thing, and then I throw it in, and I have a readout in frontal parietal, which is literally what the working memory tasks usually look like anyway. It's like high visual, high frontal parietal, which is why I think she started with that. You can see this figure really well right here at the very beginning. So yeah, I mean, I have no idea if it would work, but I mean, if it would work, I think it would be a very splashy story in neuroscience, definitely like Nature or whatever, because I mean, you're literally doing what the brain is doing, right? Yeah. If you
can
could
just speak up, people who are writing in chat, imagine that half of the visitors don't read the chat.
Yeah.
It's okay.
I'm not reading the chat. I didn't even know there's a chat going on.
Yeah, exactly. Please just speak up and let's discuss the issues.
Actually, I have a question. So this, can you hear me?
Yes.
Yeah, absolutely.
So this work they talk. I read it before too, but they talk about connection between structure and function. But how I understand it, they don't use any functional data. Their function is just a random stuff that they come up with. They only use a structure. So how can they say that? How can they discuss a structural and connection between a structural and functional in the brain when the function is just a random thing that they simulate? I don't get that.
Yeah, I mean, I'm not super happy with all the wordings. I'm not sure because they were in nature, you just end up just, throwing whatever fucking terminology you want.
Well, the
Because as
nature
I
is
said,
about.
I don't agree that this should be called a decoder and encoder. I read what her experiment is, and it doesn't really sound like that. And like her memory capacity definitely has nothing to do with information capacity. And if you have an encoding decoding model, everybody should be thinking about Shannon. Like I don't know what else you should be thinking about. So terminology is a little sketch, but
So what
I mean,
what is the point of it? That is essentially my other question. What is the point? What does this thing that they've done show it to us when half of the equation, which is the function, is just random? But what can we do with this information?
well, I think this is their main result. I think that in if you have the real brain network rather than a random one or permuted one, and you have it biased in the right weighting. And I mean, honestly, if we knew what alpha was, we wouldn't even have to run the stupid test, right? We don't really know what it is in the brain. But anyway, if you have everything set up correctly, then you can show that the real brain, conserves information like a giant reservoir. That's really what her argument is.
Yeah, I do not the thing is, I do not, when you say the real brain has two parts. It's the structure and function. We actually do not know what the function is, what the input that goes into the brain is. So when, so,
Well,
and
but does it really matter? Like, I
it
have
does.
all these connections, right? And I'm just trying to see, like, if I ring it, like, imagine the brain, very conceptually right now is an instrument, okay? And these reservoir, these connections or whatever, allow certain timbre or frequency or whatever, right? And you could imagine that if you hook it up all correctly and you're like a really terrible guitarist, right? You're not playing a tune or anything, but you're just slamming the chords. If you hook them up all correctly, then the ringing it will be the longest with the current structure. It doesn't tell you what tune you should be playing, but does that make sense?
I feel like it's a perturbation task, sort of, right? You're just kind of like looking at what if we put this in, what happens then? It doesn't matter if it's random or maybe like actual input data. That's what they assume, right? I'm not saying that I agree with that. But I
Yeah,
think they're
yeah,
like,
yeah,
what
yeah.
if we just put a
That's really
random
how
signal
that's
into the
why.
brain? What happens to the other regions? And can we infer what those regions are based on their responses to that random data? And they kind of can, because they show that the visual cortex is like very good at decoding, which we know is true, kind of.
That's, sorry, this is probably a language thing, and I'm not very well, I'm not well read in these things, but in system and signal, we have a system and then there is a signal. So one thing that we do, right, signal, for example, this is essentially what you are saying is something like signal sweeping that we do for system identification. We try to say that, okay, we break the signal into its bases and try to sweep those signals through the system to identify and say something about the system, right? But you have to have that link of the basis. You have to have the link that the real signal can be broken into these bases, right? But they have only used a random signal. I just can't see how you can say something about these results, which come from the random signals and related to the brain signal, whatever they are.
Yeah, yeah.
Which these are not the basis, right? If these were
Right.
for right, how
So,
we
yeah,
use.
yeah. I mean, no, I agree with you. Like you're talking about an impulse response to like a
Yes,
regular
yes,
system, right? And you know what an impulse response is because, well, I mean, if it's like a what is it, input output, whatever, like memoryless or whatever crap, you can take the Fourier transform and then you know exactly how it's going to respond to every signal, right?
yes.
So that's what you're referring to. Yeah, I see what you mean. I think this is like a baby step towards it,
I agree with that. I was also going to say that it's a baby step. Yeah.
It's there's obviously you can't make crazy theories because everything's connected. There's whatever, but you're trying to do like an impulse response basically here. Now they didn't really explain how much they changed the input signal. maybe, you know, certain, if it's too high frequencies, how all of this changes. I have no idea, you know. Also, what, like, they have a weird discrete time step here, which, I mean, I get why they did a discrete time step, but, you know, I rather do the continuous time version, add in the signal, and then I know exactly what time domain I'm working on. But yeah, no, but all of these are, you know.
I think the reason
Yeah.
they got away with using random signals, Ashkan, is because the results they get are intuitive. And I don't think it's the right way necessarily, but I think they were like, oh, it works and it looks good, so I guess we can publish it, even though it doesn't have any basis in terms of a real functional signal that we would normally say.
No, the thing is, the reason I ask is actually because of your question, because you saw this and said, oh, can we do this, right? Can we use fMRI? But that link, that jump is way too huge jump. And I do not see that any signal, not even EEG. EEG actually is worse, EEG, fMRI, because DTI mapping them to a real function as input and output is really hard. And I do not see how they can. They have done this actually, right? There are people that are trying to do this kind of thing.
Right, I'm doing this. It's not very different, but
yeah, but
I think you could do both at the same time.
The jump from this result to that thing, there is no evidence here. I mean, we are engineer, we can do whatever we want, but if we want, I do not see the link why this paper let us do that. Do you know what I mean? Or any paper that there are others.
Sure. I think I interjected too much of my own previous work in it. I don't think they make that connection. So they don't make the connection to fMRI. I'm making the connection to fMRI mostly because the equations are almost identical to mine. That's literally it. It's like, you know, they started with reservoir networks, but the moment that they replace their W with the DTI matrix, their equations are starting to look very close to mine. And so I realized that, hey, I can literally, you know, I can keep doing what I'm doing and just add an input signal in and just try to, you know, do a readout. And I mean, it clearly has something interesting with the structure. So maybe you can, you know, if I use both at the same time, I can get more out. That was my logic. But their logic is really just like, is the brain this?
But
that's
they have input output in your model. You have input and the previous steps of the data, right? The states.
In my model, I have fMRI input, fMRI output, next time step.
Okay.
So those are my models usually.
My point was more that like they use random data right now, and I think it's a good step. And like Amrit said, it's like a baby step, obviously. I just wonder what happens if you, whether it's even possible, because that was more my question, whether it's even possible to start using non-random data and start linking it to the sort of functional data that we acquire from the brain, and whether it still has any intuition or any intuitive results that we can, I don't know, use in our research. That was more my point, is like not necessarily that, oh, this should be the same for resting state fMRI, because I have no idea if that would even make any sense. But my question is more towards Amrit, like, okay, cool. They show that for random data, this is what happens in their model. What would happen if they used, or can they even use any functional data, temporal functional data that we can acquire from the brain instead of random data?
You know, I mean, I think that's a natural next step. I literally think that if you could show that, you would get a high-end like Nature bullshit paper. You literally, if you could do this, but with like fMRI data, and then, or fMRI like working memory task data, and you can show this shit, like I'm telling you, it would publish really high. I don't really know if it would work or not, but I mean, I'm definitely game to try it out. It's not very difficult. The only thing that I want to really
excuse me,
about a little bit is the measure here. I think I don't like this memory capacity measure. I think there might be better ways of doing it, but yes.
So, but guys, are we interpreting it slightly wrong? I think the only interesting, or like the only data there is the anatomical structure. So why are we talking about taking functional data? What they test and what they claim is that the specific anatomical structure of the brain that is different from a randomly connected network is meaningful and operates well in the criticality region. That means, to Eloy's question, let's take autism data, say, and healthy controls data, where data is not a functional MRI, but the diffusion-based tractography, the networks. And then we will see the difference in those networks by passing through the signals and trying to decode them, and looking at how long can it retain the input signal, which could be whatever it could be smooth or whatever. It doesn't have to be fMRI at all. Why is the question about fMRI? You lost me there, rather than about the anatomical network, because that's what's important here.
Right, true. But I was wondering two things, right? So you're right. So the autism or schizophrenia, I was talking about just using the structured data, not the functional data.
Mm-hmm.
But I think the second question that I had was, they do it with random data, but would it be possible to make it? I guess the point kind of is to start looking at, can we model the brain, right? In a way, like on a super high level. That's how I interpret this kind of. I mean, look, I know it's a small step, and I know it's only anatomical. The results they claim are only anatomical, which I'm fine with totally. But their idea, they're moving towards tasks and kind of trying to model the brain, right? Can we make an intuitive model of the brain that isn't like, we don't try to make it say that it's actually the brain, but that kind of looks like the brain, so that we get a better understanding of it. And then,
well, we can talk about balloon models and, for instance, TCM model that you can input stimuli, delta functions, and into this model, into some kind of a device.
Can I interject for a moment? Sorry. I'm thinking, like, to kind of get it, to the point where, like, a big step might be also having it work with kind of reproducing multivariate patterns, right? In this case, we're cycling through, like, a sequence of sort of univariate relationships. So we have, from this network to that network, and then from this network to that network, or whatever. And that, of course, again, is not really, it's definitely an interesting first step, but maybe the next step might be to see how well it does, it does the structure. And I imagine it might even be better. It might make a bigger difference in the case of reconstructing multivariate signals and, and the relationships. This is just a thought, sorry. I felt
Amrit has done something like that, but
but Amrit, do you use reservoir computing, or what's your? I don't actually.
So I mean, I like where you're going with this, because I like the idea of this reservoir, holding sort of the signals in the memory. The question is, how do we test it to get what we want out of it? And maybe you're right. One input, one output is kind of simplistic. Like, the brain is obviously has multiple processes at the same time.
And also, like, if the structure is doing something important, it's doing something important in regard, by necessity, since the signals within the brain are just de facto multivariate. It would have evolved to handle, to be tuned toward structuring multivariate signals. That's what it does. So it might be, you might find a bigger difference.
I think it's definitely a good idea. I'm trying to just think about it for the next 2 weeks of exactly how I'm going to put this into my research. But the one thing I really like is they basically, started with this reservoir idea and ended up with the same equations that we use for these brain network models, which is this giant family of equations that are trying to reproduce the brain in MRI or EEG or whatever. And, all they do is just put in an input signal. None of us do this. We just put in noise. And rather than just putting in noise and simulating with it, we actually put a structured signal in, and then do something as simple as, hey, can we just recover that thing out? You know, they're able to say great things about this. I mean, this is great. This is what I want to see. This is obvious. This is what it should be. So yeah.
Well, but back to Eloy's comment, where is your figure where you're showing what's inside? Oh, that was in your notebook. But what if this thing is just learning Fourier transform, basically? The next one, the next three plots. Yeah, maybe it is just learning Fourier transform, and that's all it does.
You know, I didn't even think of it, but now that Eloy says it, I mean, I do see fast frequencies here, and I see slower frequencies here.
And the weights, yeah. So it just that's
and some of them are even, you know, off phase, which is really nice.
It's honestly kind of like the cool thing about it is, to me, is that it's like sort of like a soft Fourier transform. That's what it looks like, right? It's not like strict.
I wish they had provided a lot more of the intermediary. You know, they have some of the reservoir states here. I don't know if you can tell here, but you know, she's only done a few traces here, you see. But yeah, I mean, some of them do look like they're faster frequencies and slower frequencies, and then some of them don't look like anything.
Oh, maybe the first one is Laplace transform. I mean, maybe it learns whatever it needs to learn, right?
But I mean, I think it would be great if you just look at the spectrum, like even like the FFT of, you know, the original signal, and then, you know, in the states here, like maybe you would be able to catch it. I don't know. I mean, that's a great insight. I mean, if I had all the reservoir states and I just applied that, I mean, you would be able to tell more. And then it would be also very interesting. Maybe you could see that visual cortex is just a higher frequency. I have no idea.
There's also the back though to multivariate in that, you know, learning the Fourier transform won't suffice. Univariate variant, right? You have to get relational phase matching, phase sync and asynchronous phases. So it's like a little, it's a more complex, it suffices for like, maybe that's what it's doing. That was a great observation. You know, like it was totally true. As soon as you said it, it was like, oh my God, right. It looks like a potentially valid observation, but it also is, you know, only sufficient because we're simply feeding it a univariate signal, and you know, a more multivariate signal. It would probably learn some Fourier components of the individual signals, but then it would have to kind of find their phase relationships and all the different kinds of phase relationships that can occur. So anyway, I shall now be. This is I don't know why, but this seems like maybe an important next step.
You could, you could with your structured signal, you could actually do like an inverse Fourier and look at how well it recovers that sort of, you know, if you try to structure, like just create like a Fourier spectrum, inverse Fourier, run the model, and then see how well sort of the activations recovered the original Fourier spectrum. If there's any relation.
And then more like, actually, shouldn't it more like you have to essentially compare the structure to, for example, FFT structure? You shouldn't calculate a structural network inverse Fourier, because you want to see that if a structure can decompose into different spectrum, right?
Oh yeah, you're right. Yeah.
So you have to compare the structural that they use and compare it to something like, we have a very good network for calculating Fourier transform or decomposing, which is literally FFT. FFT is a network. If you look at it, it's a structural connection, etc., between.
It's a tree. I object.
Yeah, it's tree. Yeah.
Lattice. Yeah.
It is a network though, because it is you essentially multiply your signal with A, which A can be considered agency matrix, right? But A comes from the basis of the Fourier. So yeah, but you should. So it would be interesting to compare that structure, but it doesn't give you anything. But compare that structure to Fourier, because Fourier is not something that nature probably use. It is not useful for nature.
No, it is useful. Nature uses Fourier all the time. Anyone using optics is using Fourier all the time. It's like we got to.
Also, your ears do a wavelet transform, which is pretty badass, honestly. but it's close to Fourier. But I mean, yeah, wavelet's even cooler. Why not? But yeah, I mean, they do have basis functions and they do project it. So yeah, I mean, maybe
we're out of time. It's amazing that Amrit, you were able to elicit a heated discussion, even though I crossed off that word in my comment. So I don't know if I will be able to match that in the next week's presentation on towards causal representation learning. But let's maybe wrap up sometime soon and meet again next week with a position paper that I will be presenting.
Great, thank you for listening. And if anybody wants to work on this shit, also let me know, because I'm definitely gonna dive into this. So if anybody's interested, just shoot me an email and chat and whatever, hang out, do some math.
Yeah. Thanks for sharing the notebook.
Absolutely, no problem.